Welcome to The Explainer. Today, we're diving into a powerful, invisible force that can literally move bridges, buckle railway tracks, and bend solid steel. And it all kicks off with something surprisingly simple, just a change in temperature. So, let's start with a puzzle, one that engineers have to solve every single day. How can a simple hot afternoon generate enough force to warp massive structures like this? I mean, really think about that. The answer isn't magic, not at all. It's physics. To really get a grip on this incredible force, we need to zoom way down. I mean, all the way down to the atomic level. Because everything we see on our scale, bridges, buildings, the whole shebang, it all begins with the invisible dance of trillions and trillions of tiny particles. I want you to imagine every solid object around you, your desk, your phone. Think of it like a tightly packed crowd of people. Now, even when they're standing still, each person is jiggling around a little bit, right? Well, atoms in a solid are just like that. They're constantly vibrating in a fixed position. Okay, now watch what happens when we add energy, specifically in the form of heat. It's exactly like turning up the music for that crowd of people. All of a sudden, everyone starts dancing with way more energy. The atoms, they just soak up that heat, and their vibrations become so much more intense. And just like those energetic dancers, these super vibrated atoms, they need more space. They start bumping into their neighbors, pushing them farther and farther away. So when trillions of atoms do this all at once, the entire object actually gets a little bit bigger. It expands. And that simple atomic behavior, that's the core principle behind what we call thermal expansion. It's this universal property of matter. You heat it up, it expands. You cool it down, it contracts. It's really as simple as that. So, let's see how this tiny atomic push builds up to affect objects in every single dimension, from something as small as a thin wire to a massive block of concrete. What's cool is that this expansion scales up in a very predictable way. If you heat up a long, thin rod, it mostly just gets longer. We call that linear expansion. If you heat a flat plate, its surface area increases. That's areal expansion. And of course, if you heat a cube, its entire volume grows. And physicists can predict all of this with incredible precision using something called coefficients. Just take a look at the table here. The base measurement is alpha. That's for linear expansion. From there, the math is actually surprisingly simple. For area, the coefficient beta is pretty much just 2 times alpha. And for volume, gamma is about 3 times alpha. It's just this beautifully predictable and simple relationship. Now, this brings us to a really common misconception. You might think if you heat a metal ring, the hole in the middle would shrink, right? It seems logical, but the opposite actually happens. The entire object expands proportionally. A great way to think about it is like enlarging a photograph. Every single part of it gets bigger, and that includes the hole right in the middle. All right, so we know this expansion happens, and we can even predict it. But the real challenge for engineers comes when we try to stop it. What happens when you try to contain this absolutely incredible force? Let's think about a scenario that engineers deal with constantly. Imagine a steel railway track on a scorching hot summer day. The sun is beating down, the metal is heating up, and it wants to get longer. But what if it can't? On the left, you see a rod with free ends. It just expands. No problem. But now look over to the right. If that same exact rod is clamped down tight at both ends, all of that energy that would have gone into making it longer gets converted into this powerful internal pushing force. And this internal force has a name. It's called thermal stress. You can even calculate it with this formula. And believe me, the force it generates can be absolutely immense. This is precisely why railway tracks buckle and why good engineers design bridges with those special expansion joints, to give the material a little room to breathe. But we don't just fight this force, we can actually harness it. This is a bimetallic strip. It's just 2 different metals, say steel and brass, fused together. When you heat it up, the brass expands more than the steel does, and that forces the whole strip to bend. This simple, clever mechanism was the heart of old-school thermostats and even some fire alarms. Now, you've probably noticed that not everything responds to heat in the same way, right? A metal spoon in a hot soup gets hot almost instantly, but the soup itself takes a while to cool down. There's a really fundamental property at play here. Think about this classic summer experience.
You've got a metal slide and a pool of water right next to it. They're both being hit with the exact same amount of energy from the sun. So why does one become almost painfully hot while the other stays so refreshingly cool?
Well, the answer lies in a property called specific heat capacity. The easiest way to think of it is as thermal inertia. It's basically how much a substance resists changing its temperature. Something with a low heat capacity, like metal, heats up and cools down really fast. But something with a high heat capacity, like water, takes a lot of energy to warm up.
And this chart makes the difference just staggering. Look at these numbers. To raise the temperature of 1 kilogram of iron by just 1 degree, you need 450 joules of energy. Okay, but to do the same thing for water, you need almost 4,200 joules. That's nearly 10 times as much energy. It's wild.
And this is basically water's superpower. It can soak up and store these massive amounts of heat energy without its own temperature skyrocketing. This is exactly why our oceans play such a critical role in regulating the Earth's climate, and it's why that swimming pool stays nice and cool on a hot day.
So, from the simple dance of atoms all the way up to the design of massive structures, thermal expansion and heat capacity are just fundamental to how we engineer our world. And it really makes you wonder, right? As we get better and better at manipulating materials at the atomic level, what new possibilities is that going to unlock?